IEEE EMBS. I'll do that again. Welcome everybody to our IEEE EMBS webinar series. We have an interesting and exciting speaker to introduce to you today. Dr. Mobashir Hassan Shandhi is a tenure-track assistant professor at ASU with a joint appointment in the School of Electrical, Computer, and Energy Engineering and the Biodesign Institute Center for Bioelectronics and Biosensors. He's also an affiliated faculty member of the John Schufelt School of Medicine and Medical Engineering. He completed his PhD in electrical and computer engineering at Georgia Tech and his postdoctoral training in biomedical engineering at Duke University. His lab is focused on developing digital health technologies like wearable sensors and computational algorithms to enable personalized health care and remote patient monitoring for patients with chronic and infectious diseases. He has received multiple awards and grants for his research work, including the AHA Career Development Award, AHA Postdoctoral Fellowship, and a Health Cardio Oncology grant. He is also an editorial board member of the MPJ Digital Medicine magazine. And today's talk is entitled Wearable Sensors and Artificial Intelligence Algorithms for Monitoring Chronic and Infectious Diseases. Welcome, everybody. Thank you to our speaker, and take it away.
Thank you very much, Andy. Let me share my screen. So you guys are seeing my screen, right? And if I click this, you are seeing the slides in the presenter mode, right? Or in the slideshow mode.
Yes, we are. Yeah. Thank you.
And you're seeing my laser pointer, hopefully. Yeah. And thank you very much for the IEEE EMBS Phoenix chapter for giving me this opportunity to share about the work we do in the lab. And overall, at the beginning, I will talk a little bit about our thought process, how we and why we are doing this sort of work and why we are very much motivated and how our works are very relevant to our current healthcare system. And if you have any particular question, any clarifying question, feel free to stop me in the middle. And otherwise, we will have more time after the presentation as well. So as Andy mentioned that my lab focuses a lot on digital health technology, namely wearable sensors and artificial intelligence algorithm for monitoring various chronic and infectious disease. So before jumping into my work of the lab, let me just share a little bit like why it is important for us to work in this space. So we all know about chronic condition like cardiovascular condition, cancer, and so many other conditions that we are here, like diabetes and etc. Right? So how this is impacting the life of individuals as well as the community at large. So 60% of the adult individual in the US has one form of chronic condition, and 40% or more people have multiple chronic condition, meaning two or more. And you can see the amount of healthcare cost that is like $4.1 trillion, and 90% of that cost is associated with managing chronic diseases. So you can understand how much it is impacting both individuals' life as well as the life of the economic status and economic condition of the country. And if you think about beyond US, like the other part of the world where there is a lot of limitation in resources, this condition is even grimmer. On top of that, with growing aging population, this burden of healthcare will actually likely to double in the next 40 years. So with this background, we are always looking for solution, like how can we manage this huge number of population, the growing population with chronic condition. And before jumping into the solution that we are proposing, let's think about how right now the current healthcare system is managing these patients with chronic condition. So overall, the idea is our existing healthcare system is battling, right? Like how we can manage more people. And we particularly saw that during COVID pandemic, like a lot of people were not getting the necessary care during COVID. And with the growing population, they're trying to look for solution that how we can manage more people into remote setting, meaning remote home care, or how can we manage more people outside the traditional healthcare setting. So before jumping into that, like let's see what happens today if in your day-to-day life, if you feel something, you feel some symptom, how the healthcare system manages that. So think about us or any individual when we are living our life, performing a day-to-day activity. If we feel something, some sort of condition, it might be some condition that is related to allergies or some other symptom you don't know. A lot of times what happens that a lot of people may have some over-the-counter drug, or sometimes the symptom may just go away after some time without even any sort of drug. And if that condition persists, a lot of time we will go to some outpatient care, maybe emergency or urgent care, or to go to our primary care to find out, okay, what can you do? So once we are visiting the healthcare system, they will run a lot of some clinical test, either in the outpatient or inpatient care, and the data is ingested in the electronic health record or medical record or EHR. And the clinicians or caregiver are evaluating this data that they are collecting to prescribe like what sort of care, like it's a medication or maybe some lifestyle intervention, they are going to prescribe that. And based on that, if the individual feels better, they can go back to the day-to-day life. If it doesn't work, then this cycle of re-evaluation and care will continue. So there is a problem to this approach. The problem is health itself is a continuous variable, meaning it's always changing, right? On the other end, we are only getting a snapshot of this individual's health in these discrete time points when they're coming to the clinic. So in other words, we are only getting very minute data points about this continuous variable that is always occurring. And although we are talking about healthcare, we are actually in the patient care, meaning we are always being reactive in this sense. We are waiting for something to happen, and then we are trying to intervene. So a lot of times we miss that opportunity to be proactive, to find out what is going wrong before we are seeing the symptom. Because a lot of times, once you are seeing the symptom, that means something already went wrong or something is decompensating or deteriorating. That's why you are feeling a symptom. So can you be more proactive? So that is the idea of this remote patient management, personalized healthcare, and providing, being more and more proactive. So to do that, what can we do? So we have been seeing a lot of wearable sensors or other technology that we can leverage. Even our smartphone has a lot of sensor. We can even record our day-to-day life activity there. So idea is we can leverage this ubiquitous sensor as well as the wearable that we are developing in the lab as well, that we can collect the data of this individual, both in their home when they're healthy and performing the day-to-day activity, as well as when they're sick or they're feeling some sort of symptom. And by doing so, we can get more information about their life and their physiology from their real-world scenario. And we can ingest that data into biomedical signal processing and machine learning algorithm to extract the key feature or clinically relevant information that we can incorporate into existing clinical workflow. So by doing so, we can provide the clinicians and caregiver additional sets of data. But what sort of data we want to share with them, because they're already overwhelmed, that's also another question that we need to think about, like what are clinically meaningful for them. And by doing so, hopefully we can close the loop of healthcare system. That is the idea of our work in the lab. So I already talked about that the major or main objective in our lab is to focus on personalized healthcare and remote patient monitoring, or in a nutshell, how we can close the loop of this healthcare system using a solution that either we are making, or it can be both from the hardware as well as the algorithm perspective. So in our lab, we actually work a lot on development of biomedical sensor. We're talking about embedded system, particularly that we work in the lab, as well as we use commercial wearable, namely Fitbit, Apple Watch, Oura Ring, and other commercial wearables, as well as some research-grade wearables as well. And we use this sensor, either the one that we are making or the one that's already available in the market, to collect this physiological signal or healthcare information from the individuals. Then we use or develop this signal processing and machine learning or AI algorithm to extract this valuable or clinically relevant information and predict certain health outcome or track some health outcome. So both this hardware and the algorithm-based solution, we generally validate them against the clinical gold standard, because we always want to make sure that whatever we are doing, it makes sense clinically. So at present, we are mainly focusing on how we can validate both the hardware as well as the algorithm piece against clinical gold standard with our collaborators from various healthcare systems. And finally, we talked about this remote home monitoring, right? So we want to validate this technology in the remote home monitoring space as well. On top of this work, the other thing we also focus a lot is sometimes as we are working on these different sorts of biomedical or physiological signal and this wearable sensor, we are not always sure why these sensors are working and how these sensing signals are related or connected to the underlying physiology or pathophysiological condition, how they may vary based on certain disease condition or certain disease phenotypes. So there's a lot of thing we still don't know about that. So we are also investigating these generative factors of this wearable sensor or physiological signals that we are collecting from the lab. And finally, once we are try to verifying and validating these technologies. We want to make sure that we are verifying and validating this technology against a representative population to ensure that our methods, both hardware and algorithm, are robust enough so it can work equitably across the board. So with that background, let me start with the first part of my presentation, where we're going to talk a little bit about how we think about developing digital technologies for monitoring and tracking chronic diseases. So there are different clinical outcome that is very relevant in this particular space and clinical condition. We work a lot in cardiovascular health. And in cardiovascular health, one of the key clinical outcome that the clinicians are very much interested is cardiorespiratory fitness. So it is just the capacity of our overall cardiovascular system to supply oxygen to our peripheral muscle to perform day-to-day activity. And a low, so this is known as CRA for cardiorespiratory fitness. And if you sometimes your Apple Watch or Fitbit gives you some sort of cardiac score, actually they are referring it to this CRF score in general. So a low value of this marker or this cardiorespiratory fitness is a very strong predictor of cardiovascular disease and all-cause mortality, even with adults, like without any sort of condition. So very, very important marker, like patients with heart failure and other cardiovascular condition. This is a very important marker for them for prognosis as well, and tracking the disease condition over time. So the way currently this is measured is this patient has to go through some of these tests known as cardiopulmonary exercise testing, and they will put some mask on them. They will collect how much oxygen they are consuming, how much carbon dioxide they're exhaling, so also known as gas exchange variables. And by doing so, they will go through some sort of routine or clinical exercise routine known as maximal exercise test. So it will be graded. So they will increase the difficulty level of that exercise, meaning that more intensive it will become, and they will push you towards your limit, and they will measure what is the maximum oxygen you are consuming. That means maximum oxygen consumption and delivery that you can have in your system. So that is known as the VO2 max, and this is one of the objective marker of this cardiorespiratory fitness. So as you can imagine, like to have this sort of test, you need trained professional and a lot of this technology like this metabolic cart, right? So it is not a feasible solution to collect this sort of data in real world. So there are some portable gas analyzers that can provide you similar information, like not only Cosmet K5 and then VO2 Master Pro, but you can still see like these devices have this mask. On top of that, they are very, very costly. Like VO2 Master Pro, it is like cost around, I think, 8K, but this Cosmet K5, which is people treat this as a gold standard in this space, particularly for portable gas analyzers. This cost 50K, close to that. So think about, do you want to measure this very important marker for cardiovascular health, and it costs 50K. So it's not possible for us to use this sort of device for personal health monitoring in general, right? So with that background, we are thinking that, can we measure this cardiorespiratory fitness from wearables? We are seeing that these wearables are providing us information about cardiac score or fitness, so how well that is. So actually this stat needs to be updated. So we have, I think maybe at this time, 1/3 of the people in the US, even close to maybe half of the adult individual in the US has some form of smartwatch or wearables at this point. And these devices use some optical sensing like photoplethysmography and accelerometer and other sensing and other information like demographics to give you some sort of score for you that what is the cardiorespiratory fitness. So can we leverage these wearables? How much can we trust them with respect to cardiorespiratory fitness? So the short answer is unfortunately no. Multiple studies has demonstrated that although their heart rate measurement is generally good during sedentary activity, not like when you're moving, but if you are just staying very still, the heart rate measurement, like during sleep and without not a lot of motion, the heart rate measurement is pretty good. However, the energy expenditure measurement, that this cardiorespiratory fitness, is very poor. Like the error rate is in general 30 or even more percentage. So as you can understand, that their measurement is very erroneous, and we cannot trust this sort of measurement for cardiorespiratory fitness. For the heart rate, as I mentioned, if you are not moving, then heart rate measurement is pretty good, like during sleep. But if you are active, like performing some sort of exercise, then the heart rate error actually goes up 30 or even more percentage in that sense. So with that background, our thought of this work was, can we develop a more accurate and low-cost multimodal wearable sensing system that can assess cardiorespiratory fitness? So when you're thinking about that, what are the challenges of the existing wearables? The problem with the existing wearables are if you even go back to this previous slide, they are mostly a wristwatch-based solution a lot of time because it's user-friendly. The problem is they are actually only getting the information from the periphery, and they are not getting the total information, or it doesn't capture the overall cardiovascular system and the health of their system too well. And the way that they measure the VO2 max particularly is using some sort of heart rate-based model. At least that is our assumption. So it's not it doesn't work well in a population level. That's why like there is a lot of error that you can see here. So as an engineer, when you're developing any sort of sensing modality, always the starting point for us is we start to think about like what's the problem we are trying to solve. And this is the way we think in the lab as well, that, okay, let's define the problem. So we want to measure here the VO2 or oxygen uptake, how much oxygen you are consuming, right? That's a variable of interest for us. So once you understand, okay, this is the problem or this is the actual parameter we are interested about, now let's think about how it works, meaning how physiologically they are relevant to underlying physiology and what is the governing equation of that particular phenomena. So we are talking about, this is a fixed equation, which is the governing equation of VO2. So let me explain a little bit what is talking about here. So VO2 is a product of the cardiac output and the arteriovenous oxygen difference. So cardiac output is the amount of blood your heart is pumping in each minute. So amount of blood heart is pumping in each minute. And the arteriovenous oxygen difference is the difference in concentration of oxygen in your arterial and venous side. Meaning your arterial side is actually the side which is delivering the oxygen to the periphery, and the venous side is the return of that blood to your heart overall. So the difference is between these two systems is the amount of oxygen your muscles are actually using or utilizing. That is that parameter. Furthermore, like this cardiac output is a product of stroke volume and heart rate. So stroke volume is the amount of blood your heart is pumping in each heartbeat. And you're multiplying with heart rate, meaning number of heart beats per minute. Multiplying these two, you are going to get that cardiac output. So this is the governing equation of VO2. So, okay, we understand, okay, this is the physiology, right? How these input variables are connected to the outcome of interest for us. Then what we do, we need to think of like, okay, these are the input variables of my equation. So what are the existing non-invasive signals, or maybe you have to come up with your own solution that can help us to estimate or measure this phenomena, either directly or indirectly. So there, for example, if you think about you want to measure heart rate, ECG or electrocardiogram is a gold standard to collect heart rate data. You can also use photoplethysmogram that's commonly used in the commercial wearable or other sensor as well. So then if you think about the stroke volume from our own work, as well as a couple of other work in the space of research, people have explored these various forms of other physiological non-invasive sensing modality known as seismocardiogram, impedance cardiogram, gyrocardiogram, ballistocardiogram to estimate changes in stroke volume. Or in summary, from these different sorts of physiological signal, you can get information about the stroke volume. And in terms of the arteriovenous oxygen difference, like photoplethysmogram, near-infrared spectroscopy sensor can be a good candidate for those. So, okay, so we can see that there are multiple candidate physiological non-invasive signal that we can use to measure or estimate this key variable of this equation, right? So hopefully if we can combine or make a some sort of combination of this technology, maybe we can get VO2. That is the overall thought process. So are you going to use all of them? No. Based on this understanding of physiology and the requirement of our application and the form factor, we can choose like which appropriate sensing method, because that will determine the form factor, where you want to place the sensor. All of this we need to think about. So we can select some appropriate sensing method for that given application. And finally, once we select that, we start to develop like technical design, like block diagram, how all of them are connected. And from there, once we have that design, we start with benchtop system. Like we use BioPack and other data acquisition unit where you start talking about or working on this idea on a benchtop system where everything is still connected with wires. And once we see, yes, our idea is working, meaning we are able to collect that data, and we may do some sort of initial algorithm development using that benchtop data to ensure that our idea is working. Once we see that, then we move to more portable version of that, meaning we are then making them more and more smaller. Still, there are some wires, as you can see, but it's a portable one. You can wear it, you can walk around. And finally, once we are done, having more understanding, we move to more wearable. That is, there's no wire coming out, so you can like snap it and you can put it on the individual. They can walk around and we can collect that sort of a physiological signal. So once we have that, the general approach for us is we then put this sensor on the healthy individual to begin with, and then we start collecting data from them and try to estimate those sort of a variable of interest for us. So this was a study during my time at Georgia Tech I conducted, where we are collecting this physiological signal from the wearable patch that I mentioned. And this is the gold standard, that VO2 we are talking about, that oxygen uptake during activity. So you can see that 50K device on an individual. So for this study, what we did was we collected data when the individuals were walking and jogging on a treadmill. That was more of a controlled activity. We had to set a speed, and we asked them to walk around the Georgia Tech campus. You can see the Georgia Tech campus here. There's a lot of uphill, downhill stairs, and we wanted to measure this VO2, how much oxygen they are consuming. And our goal was to estimate that VO2 with this non-invasive sensing modality only. And this is just a figure of that protocol I mentioned. And the first part was that controlled activity on the treadmill, like walking at 5 different speeds, 6 minutes each. We had a recovery. Then we had some like gap between the protocol. And then the next was they're walking around that campus and they are maintaining their own speed. They are following the traffic rules and everything, whatever they need to do in the day-to-day activity. So let me just show you some of the signals we collected from that wearable sensor. So we collected a single lead ECG or electrocardiogram sensor, and we collected 3 axes of the seismocardiogram or SCG signal. That is a vibration of the chest wall that carries information about when your heart valves are opening or closing. So you can get information from this vibration signal as well. Then we do like traditional signal processing, like digital filtering. And then we segment the data into individual heartbeats from this ECG R wave or ventricular depolarization. If you're familiar with that, then we segment this into heartbeats, and then we do some sort of ensemble averaging to reduce the noise in individual beat. In this way, we can have a higher SNR or signal to noise ratio, and we get clearer beats where we can extract different sorts of marker or feature from this signal. So then once we have this more cleaner signal from this individual heartbeat, we extracted different features like time domain features from them. And on that end, like this is a list, feel free to check the paper if you're interested. These are different time domain, frequency domain, and power feature that we extracted from these different signals as well. So the idea is that for us, we are getting this time series data from our wearable sensor. We are also getting the time series data from the VO2 device, that COSMET device, that is the gold standard that we are trying to estimate from our sensors, right? So we have this time series data, then we are segmenting the data and then extracting the features from the segmentation, and then trying to understand how they're related and how we can use this wearable signal to estimate that gold standard data. And there we are using machine learning to be more exact. And in this particular work, we used extreme gradient boosting, XGBoost, and we use leave one out cross validation, if you're familiar with that approach. And what I'm showing here is the result of our study, both with the treadmill protocol, the controlled activity, and outside walking, which is more of a representation of activities of daily living in this. And you can see that I have separately, this is the top row. If you see, this is the result from both the sensor we are making, meaning the vibration, and the heart rate based model, meaning I'm using features from both the vibration signal as well as the ECG or heart rate. And we are just comparing them with, if you only use heart rate based model, what will be the performance? The reason for that comparison is, as I mentioned earlier, that majority of the commercial wearables, they actually use some sort of heart rate based model for their VO2 max estimation. So we wanted to see that, okay, how our algorithm, which is using this additional sensor that we are developing, and compare that with the more traditional heart rate based model. And as you can see, the R square and the RMSE value of estimation, so our method is significantly better and compared to this heart rate based model that's commonly used in commercial wearables. So as I mentioned, this heart rate based model doesn't work well in a population level. And if we compare the performance between treadmill and outside walk, obviously treadmill was a controlled activity, meaning everyone was following the same protocol, where outside walk, everyone was following their own speed, traffic laws, given time, and the environment or weather, which is hot or milder temperature at the time in Atlanta. So it was much more variable and heterogeneous. So our performance of our algorithm was a little inferior, which is expected because it's more real world scenario. But still, you can see the comparison between heart rate and base model. Our model with using our this multimodal sensor was significantly better compared to more traditional heart rate based model. The one I wanted to show you, actually the time series data from this study. So I'm showing a graph on this middle one is the best case scenario for the outside walking. Let me explain a little bit what is happening here. So the blue solid line is the gold standard VO2 data, meaning when they are walking outside in the Atlanta or the Georgia Tech campus, this is the VO2, the time series data. As they are going uphill here, so you are consuming more and more oxygen. There is, I think, some rest stop for a traffic, so they're stopping. So you can see it's going down, and this is where they're going downhill. So the amount of oxygen you have to consume is less. Then again, they are going back uphill and then going back downhill. So you can see that it's a real world scenario when they're actually walking around the campus. And the estimation is that red dotted line from our model, and this where my cursor is a best case prediction for our algorithm amongst all the subjects. And even in the worst case scenario, like you can see that although there is a R square is not good, but you can see why. Because overall, the sensor or our algorithm was able to track the changes in VO2 very well. But there is a DC offset between the actual value and a predicted value. So one thing we haven't done in this work initially, we have not done any sort of personalization or calibration for individual when we are running this algorithm. So what it is telling us, that is this graph, that yes, we can track the changes very well, but we may have to do some sort of personalization of the model or calibration for the individual. So if we do so, then our estimation would be even pretty good for this individual as well. So overall, it is showing us, yes, we can do very good in terms of VO2 estimation in healthy individual. So with that, then our next case is, okay, if it's working well in healthy individual, can it do it on people with cardiovascular diseases? The short answer is yes. That's what we did the next. So we actually collected similar data from patients with heart failure when they're going through this routine clinical test at UCSF at the time. We collected data from 68 patients with heart failure with reduced ejection fraction. And actually, the part of this test, they go through this routine exercise test. And based on this test, they actually get some sort of recommendation is whether they require any advanced heart treatment, namely like whether they require heart transplant or heart pump, also known as left ventricular assisted device or LVAD, some sort of. So they are in a very decompensated position, meaning so their chance of mortality is very high actually in this population. So as a outcome of this test, they provide this sort of outcome that whether they require heart transplant, meaning their heart is failing, so they cannot sustain their day-to-day life with their own heart. So they are becoming a potential candidate for heart donation eventually. They're waiting in line to get a donation from heart from someone. So as you can imagine, this is one of the tests that they routinely use. So once we got that data, we separated this data set in a training testing set where we developed our model using a leave one out cross validation. And we had a completely independent validation set, which was collected after we developed our model. So our algorithm never saw this validation set result when you're developing that. So we collected that data afterwards. So I'm only showing the result from the validation set that was collected afterwards, where you can see that in the left one, it was a estimation of this VO2 when they're going through this routine clinical test, that how much oxygen they're consuming. And out of the 24 subject, the R square was 0.76. So given this is a heart failure population, it is pretty good and a very strong result. And on the other end, as I mentioned, as an outcome of this test, they provide a recommendation whether they require any advanced heart treatment. So our work was, this is more of a prediction, a classification task, to see that can you predict that outcome of that, what will be the recommendation from the clinician only based on the wearable data. And our model was able to predict that outcome with very good accuracy. So the area under the curve of this receiver operating characteristics curve was 0.92. So this is pretty good. And one self promotion here is like, what's the next step, right? So what we saw actually on what I did during my time at Georgia Tech, the technology that I worked on and even the algorithm that I developed, eventually there's a company that formed from my PhD supervisor's lab where they actually validated the algorithm that I developed in a larger population with heart failure. And they recently got the FDA 510K clearance from that. So the work we started from the bench, we are right now actually translating the whole thing into the actual patients with heart failure. So this is a like great motivation and success from the work that we do in the lab, particularly. Now let me switch gear to the current work that you're doing at ASU, particularly. So we are working a lot on this space with the wearable technology to track cardiorespiratory fitness in heart failure. And we recently got this American Heart Association Career Development Award. We are working with Mayo Clinic here. So idea for us is how can we leverage the wearables that we are developing as well as commercial wearables to come up with this closed loop system eventually. That is the future we are looking at. And in between, what we are doing is validating the wearables that we are developing to monitor and track cardiorespiratory fitness. That's the work we are doing. And we are collecting data from individuals when they're walking around in the campus, as well as they're going through some sort of routine clinical test, like on the treadmill or a bike. And we are collecting a lot of data from them as well. I will not share more about this because it's an ongoing research. Hopefully, in the next couple of years, you are going to see more result as we are collecting data from both patients with heart failure as well as healthy individual. Another major project we are running in the lab is focusing on these generative factors on the wearables and working on developing digital twins. We are actually recently got an internal grant from Mayo Clinic on that idea. Again, I'm not going to share too much about that work because it's ongoing and very early stage. So we are focusing a lot on the understanding the generative factors of these wearable sensors and how they're related to underlying physiology and pathophysiology, and developing digital twin for cardiovascular health and other conditions as well. If you're interested, I'd be happy to discuss more offline about that, but it's an ongoing study. And hopefully, we are going to see more work on that front as well in the near future. And another ongoing project that is happening in the lab is focusing on sleep apnea, particularly. I don't know how many of you are familiar. So sleep apnea is a condition where your like muscle at the back of your throat might close down partially or completely. This is a very much underdiagnosed condition, and it has a lot of downstream impact on cardiovascular health in the long term. And this is a condition where a lot of people can also have daytime sleepiness, and they can go through some sort of like accident, like vehicle accident or other condition, eventually like developing cardiovascular condition. And this condition is heavily underdiagnosed. So we are working a lot with Mayo Clinic here as well, where we are developing AI/ML algorithm as well as for predicting this sort of sleep apnea, both from as well as tracking the sleep health over time in the individuals as they're going through multiple of these clinical tests. And eventually, we want to focus how can we develop like wearables to monitor their physiology in their day-to-day care, so we can track their health, their sleep health, particularly in their remote home monitoring as well. So I will actually switch my presentation to the next phase of my talk. Are there any particular condition or any question that you guys want to ask in between? I'm seeing one hand.
Yeah, go ahead and put your questions in the chat, and then we can read them and see. We'll give it a couple minutes there. Is sleep apnea a cause of snoring? Do you want to take that?
Yeah, snoring is one of the marker actually to see what is happening. Yeah, this is one of the symptom.
Yep. Other questions? And we'll have another shot for questions at the end. But for now, I think we'll go ahead and proceed. Sound good? Oh, one more. Is there a recommendation for affordable IMUs wearables? You mean ones that already exist, I'm guessing is the question.
So there is no, I think, short answer, right? So there are obviously different affordable solution, but it will depend on the particular application. So what you are looking at, and that is something we are always talking about, that you have to understand the application and potential of this particular sensor for that condition. Like if you're talking about cardiorespiratory fitness, you have to understand that what condition you are trying to measure, what the physiology and pathophysiological like phenomena you're trying to measure, right? Then you can understand it better. And the wearable and AI, there's a lot of hype around that, but you have always need to understand the potential and there are limitation as well. So like it will be a longer conversation for a particular application, but definitely there are solution that is showing a lot of potential, but you have to understand that there are limitations as well.
Good questions. Let's go ahead and proceed, and then, like I said, we'll pause for questions again at the end. Thanks.
Sounds great. So yeah, let's switch gear to talk a little bit about how we can leverage this digital technology for infectious disease. So this is some work that I did actually during my postdoc at Duke. So I started my postdoc during COVID, and we still all can remember like what was our life during that time, right? And we saw that we had a lot of diagnostic testing shortages very early on in the pandemic. On top of that, we have even saw the similar issues when the new variants like Delta or Omicron hit, right? And we still remember like we had to wait for multiple days, or even I remember to wait in like lines to get tested because we are not sure if you got exposed or something, you know. So we all remember like those days of and it's like it feels like a movie, right? Like the way we led our life at the time. And on top of that, when this initial COVID pandemic, the early stage, we also saw that there's a lot of disparity, particularly in the rural communities where there's a lot of shortages of diagnostic testing. So when this is unfolding, so at the time at Duke, we were thinking about like, in this scenario, how can we leverage this digital technology, namely like wearable sensors and smartphone, to improve access to healthcare, particularly in the resource limited setting? Because wearables and particularly smartphone is ubiquitous, right? So how can you leverage this? So when you are thinking about this, we came up with this idea of intelligent testing allocation, or in short, ITA system. Let me just explain a little bit about that. So think about you have 30 individuals on that given day that comes to you for testing, that they want to test for COVID, but you only have 9 diagnostic tests available to you. So think about the early stages of pandemic where we had limited testing, right? So we cannot test everyone. So how can you choose 9 individuals from these 30 people on that given day? So if you just choose randomly, that is a random allocation, you may end up only getting like 1 person maybe positive out of that, because there's a prevalence of the disease in that population. On the other one, what we are thinking at the time is, because people have wearables and a lot of people and almost everyone has some sort of smartphone, if we can use that sort of data that you can collect from those devices, as well as we can collect their symptoms from some survey or some other means, we can come up with a subpopulation based on this sort of real world data to come up with a subpopulation who will have higher likelihood of being tested positive for COVID on that given day. So from that likelihood, we can choose like which people we want to test, because we have limited testing. By doing so, we can increase the number of people who will come back positive using our limited testing capability. Or in other way around, we are using these limited resources more wisely or intelligently. That was the idea of this intelligent testing allocation. So for doing this, at the time during pandemic, we had this study from Duke, lab, the Big Ideas lab at Duke, the peer that Ghislaine done. And we are running a study known as Scope Identify, where we are asking the individual to donate their personal device data and fill out some daily survey of symptoms. So we are collecting a smartwatch or daily surveys, and all this data were ingested into a Microsoft Azure platform, where we extracted the digital biomarkers, namely heart rate, activity, sleep, like sleep duration, and the symptoms from there. And once we got all the data, you can see that the number of subjects we had in the study overall. So we had more than 7,000 individuals consented, and close to like 6,700 people completed the initial survey. One thing to note here, it was not a mandatory condition that you have to have a wearable to be a part of the study. We want to just survey like what is happening, what is the current status of the disease, and out of them, and you don't have to have a test to be a part of this population as well. So like roughly 1,300 people reported of diagnostic testing. And out of that diagnostic testing, this number of like we had COVID positive and negative. And you can see the demographic breakdown of that. Other thing to talk about is it is not a requirement that they have to have wearables, right? So a lot of people also we have in the study, but majority of them may not have wearables. Also, even they have wearables, they may not they were not wearing their device maybe when they were sick. So there's a lot of missingness in the real world data as well. So I just wanted to show you a picture of like where these participants actually came from. So you can see all over the US. Duke is in North Carolina, so obviously a lot of population from there. We also have population from like UK, some other countries in the Europe, as well as India and other places as well. So it was a very much international study, and obviously we had a lot of representation from the US. So once we get all this data, as I mentioned, we curated all these different type of data like Fitbit, Apple Watch, Garmin, you name it, and there are a lot of missingness as we were trying to align this and finding out the relevant data that you can extract. So we had to spend a lot of time on that process. And then we performed some sort of exploratory data analysis, extracted the feature. Then we actually developed that ITA model using some sort of machine learning. And that model gave us that likelihood of individuals, likelihood of being tested positive for COVID for a given day. And we can rank them with respect to their likelihood. And I'll talk about that later in the slide as well. So let me just briefly show you how that data looks like. So this is the data that's coming from, so in a machine learning like space, you know that we generally separate the data into training and testing, and we explode all our features from the training set, and we have not touched that test set particularly. And finally, once we develop the model on the training set, we validated our algorithm on that independent test set. So the data I'm showing here is only coming from the training set, where we did the exploration of the features. So the data is coming from 50 individual with COVID positive diagnostic testing at the time. And you can see their daily steps count and resting heart rate in these two plots. And this purple dotted line is the actual diagnostic test date. And what we assume at the time that roughly 21 days before the test date, we are calling that as a detection period, meaning we want to detect that disease before that, right? And the reason of like why we chose that 21 days, if you remember at the time that FD and others were, CDC actually talked about at the time that the COVID-19 may have an incubation period of 2 weeks or so. And we also thought of like maybe some people are started to feel some symptom, but there'll be a delay between when they're seeing a symptom and when they are going to get that actual test of the diagnosis, right? So we had like another 7 days. So that's 7 and 2 weeks. That is a total 21 days we thought of the detection period that most likely they got infected somewhere in that ballpark. And we wanted to see that how soon we are seeing some sort of signals in them. And before that detection period, this is the period like after 41 days, we are assuming that they were not infected at the time. And most likely we are using that as a baseline of those individuals. So it's an average across participant. What you're seeing that once most likely they got infected somewhere here, their bodies started to fight, and we are seeing a rapid increase in their heart rate, resting heart rate is significant. And also we are seeing a significantly decrease in their daily activity, right? So we are seeing, that means there is some signal that is happening before they are diagnosed with this COVID-19 disease. On top of that, we are trying to understand, okay, we are seeing some signal in COVID positive, but what about COVID negative? Are you seeing something? So yes, this is the data is only showing the orange is COVID positive group, blue is COVID negative group, and I'm only showing the deviation from the baseline. So 0 is the baseline, deviation means how much resting heart rate is changing. So you can see that, and -1 meaning 1 day before the diagnostic test date, -21 means that 21 days before the diagnostic test date. So obviously, most likely before like almost 1 week or 2 weeks before, they don't have any sort of disease or maybe no symptom as well. So the two distributions are overlapping, but close to the diagnosis test date, most likely they have some infection maybe here, and we are seeing the deviation between COVID negative and positive group here as well. We are seeing similar in the steps as well. So what is this figure is showing us that there is some signal, but it depends which part of the data you are looking at, right? So we are trying to find out like, okay, in the real world, we can look into some part of the signal, but how can we choose like where we should look at, right? So unfortunately, the papers before us, majority of them just arbitrarily choose some days to look at, and without giving us any sort of rationale that we need to choose that day or this day, why they're choosing. So they actually arbitrarily chose certain value or some parameter without giving any sort of rationale. The problem of that sort of method is that work will not be reproducible. If you want to apply that same idea on your data set, it will not work because it is just an arbitrary value. So instead of going that route, we actually went through some data-driven and domain-driven understanding of that. So what do I mean by that? So we segmented that data into different buckets, and we try to explore which segment of the data will provide us the most significant features between COVID positive and negative from this training set. So that will be our window, and we can choose okay, this is the window our data is telling us from the training set. We should look into that part of the data. So we can feel free to take a look at the paper if you're interested. So the take-home message is from this grid search method, we are able to pick the portion of the data we should look at to extract the feature from the signal. So you can apply the same method in other data set because it is a data-driven method, and you can follow that same step on your particular data. So once we have in total 40 different features from the steps-based and resting heart rate-based features, we put them in a machine learning model, and then that model was giving us that likelihood of being tested positive for COVID on the given day. And here I'm only showing the result from the training set at the very top row. I'll show the value for the test set as well. It is showing the very traditional receiver operating characteristics curves and the precision recall curve. If you are into machine learning, it should be very reasonable, or very familiar term for you guys. And you are seeing three different lines because we have stage-based feature, resting heart rate-based feature, and combination of the features. So the three lines are showing that if you only develop a machine learning model using only steps-based feature, like how many steps you're taking, or only resting heart rate-based feature, and if you combine both of them, how the model will perform. So you can see that, yes, so we are able to show the potential of this model, and the values we are getting was comparable to the other papers at the time we published our results. So it is very much within the range of other research as well. So the major take home for us was actually the last figure. So as I mentioned, this machine learning model was giving us a likelihood of being tested positive for COVID on that given day. So if we rank the individual and choose that how many people we want to test for and who to test on that given day. So let me explain this, what is this figure is mentioning. Think about, you only have 50 diagnostic tests on that given day. And if you choose 50 people randomly from this population of 227, based on the prevalence of this disease, you can find the prevalence from the overall population. You may only get 15% or 15% of the people will come back positive if you just pick randomly. But if you use our rank list from the model we are getting, that ITA rank list, you can almost double the number of people who will be positive from your diagnostic test. So you are better utilizing these limited resources. Now think about, you have only 10 tests available. So kind of here, even our model was able to improve that positivity rate, like how many tests will come back positive from this limited test, was 4 or 5-fold higher than random allocation. So this is showing the potential of our work. And the last row is showing the result of that, when we validated that on the independent test set separately. Yes, we are also seeing the potential of our work on the independent validation set as well. And the key take-home message for this work was our model was able to improve or increase the positivity rate of this diagnostic testing in that cause-validated training set up to 6.5 times, and in the independent test set up to 3.5 times. Another key take-home or very crucial result for us was our model was able to even capture people who were asymptomatic at the time, meaning they did not have any sort of symptom. But our model was able to just capture from their physiology and activity data. And they were saying that, okay, you should test that individual if you have this many tests available for you. So it was a very, very crucial result for us. The result was published in the Nature Digital Medicine. Feel free to take a look at the paper. And we also saw that some of the resting heart rate feature were becoming significantly different between COVID positive and negative 10 days prior to diagnostic test day. So we saw some signals as well. And still this feature became significant later. And we had some follow-up work. I don't know whether this paper got published from the NIH Recovery Initiative, which was the long COVID initiative. They're working on that. And hopefully you guys are moving to see more results from that work as well. With that, let me try to wrap the presentation today. So we talked a lot about the research direction in our lab. In our lab, we work a lot in biomedical sensor development as well as developing of the signal processing machine learning algorithm. And we validate this technology in the gold standard, clinical gold standard, as well as we validate them in the remote home monitoring setup as well. And we have multiple open position in the lab. Both we are looking for very motivated PhD student. If you are in the you are looking for PhD position, definitely reach out. And if you're also a master's or undergrad student, that will be relevant for ASU student actually, not maybe for other schools. But we are looking for PhD student. We're also looking for postdocs as well. So if you are in the market and you're looking for a good position, both on the hardware side as well as signal processing or AI ML side, email me your CV with a short intro, and you can get more information on our web pages as well. With that being said, thank you very much, IEEE EMBS Phoenix chapter, for giving me this opportunity to share the research we do in the lab. I'm happy to share more in the future, and I'm happy to connect to you and happy to answer any particular question that you may have. Thank you.
Well, thank you. Thank you very much for that informative talk. We do still have we have a few questions already, and anybody else, if you can just add your questions to the chat, I'll take them in the order they were received, and we'll see what we can do. So the first question, I think this is referring to the for the infectious disease part. Is the center receptive to or seeking new relevant projects? And if so, who is the contact point? And if you need to clarify that question, you can do it. Is that clear to you?
I'm not sure if he's talking about any particular project or in general. So if you're talking about in general, then I feel free to contact me and we can definitely talk about which project or area of interest that is relevant to you. We can have a lot of discussion. So at this point, we are working a lot with Mayo Clinic Phoenix, Mayo Clinic Rochester. We're also working with Honor Health here in the Phoenix area. And we also have collaboration with Duke, UCSF, Emory, Northwestern. So we have a lot of collaboration with clinical partners. We're also working a lot with different commercial wearable companies as well. So there's a lot of ongoing project that is happening in the lab, both with industry, academia, and even federal agencies as well. So I think it might require more discussion on a particular project, or if you're looking for something like that.
Yeah. So multiple answers. I guess the best one on that is to reach out. We should you should be able to have the speaker's email available through the through the registration link. If not, you can just reply to this EMBS general email who's sponsoring the event, and we can get you in touch correctly. Okay, the next one in the chat here is referring to the COVID testing results, and is it statistically significant? And did you cross-validate? So it's a good question, right? You said the data says you predicted more positive results, and I think the gist of the question is, were they really correct positive results, and statistically so?
That's a great question. And the short answer is yes, we have actually all that. When you're talking about significance, I'm talking about statistical significance. And we ran the test and we saw that. And we ran all this exploratory data analysis and statistical testing on our training set data. And I think the follow up question was, did we cross validate? So when we developed this machine learning model, particularly after we ran that statistical analysis, and the paper has more details on that, we used nested cross validation on the training set. Nested cross validation actually further helps you in terms of hyperparameter tuning and cross validation together in one go. So we use that on the training set. And on top of that, we did separate validation on the independent test set of our machine learning model. So yes, we have done both the statistical analysis as well as the cross validation that you're talking about.
Right. So the key there is you have to have a gold standard to compare to, right?
Correct.
And yes, the answer is you did do that. You had all those gold standard results that you compared to and confirmed. So excellent. The next question here, are you saying we're able to predict infected people based on their activity levels and resting heart rates? And I think I know
Yeah.
the answer, but why don't you go? Yeah.
Yeah, that's a great question.
Yeah.
Short answer is no. Meaning we were able to see that if something is deviating from your baseline. And meaning what? Like if you ask me that am I infected with COVID or flu? I don't have the specification. But if you ask me something is going wrong, do I need to be tested? We were able to predict that. Like, yes, you should be tested, given like in this scenario. So from these wearables, we cannot directly say what particular condition you have, meaning this sensing modality are sensitive, but not very specific. So you cannot differentiate like whether you have COVID or flu or something else is going on. So what we saw that someone's baseline, they are deviating from their baseline, meaning their resting heart rate is deviating statistically significantly by a certain number of beats from their baseline value. Their steps counts was deviating or reducing significantly compared to their baseline. And from there, our machine learning model was able to predict like who should be tested on that time. But if you're asking that, am I infected with COVID? Short answer is I don't know. What I can only say with that technology is like something is going wrong. You should, and based on this, like who is more likely to have that condition, that is what we are talking about. If you're asking the specificity, it was not for that particular purposes.
Yeah. It's kind of to guide who you should be testing, in other words,
Correct.
right? Yeah. And so the follow-up there, it said if so, but I think it applies even if the answer is not, how were the people selected for the population that you were investigating? So clearly you had to pick which ones who you chose to select to do the experiments on. How did that go?
So it was a real world data, and we call it like opportunistic sample. Whoever donated their data for this purpose,
Ah,
we have not excluded any individual. We only focused on adult individual. There was no limitation as such that you have to be in this category or that category. In the real world data, as I mentioned, that there's a lot of missingness. So those constraint actually impacted who we can include in our
yeah,
analysis. So it was not anything regarding race, ethnicity, or as such that we use for our guiding criteria. It was more about do they have enough data for us to develop the model? And I
right.
have talked about that in the paper that how much data is enough. So we did some sort of, again, grid search method that I haven't explained too much here in the presentation to choose a certain population for us. That was mainly based on the availability of that data itself, not
Yeah.
any other criteria of the disease condition or the race, ethnicity, or any other demographic factors.
Excellent. So blind from your point of view, but the people had basically had to opt in, right, and give you
Correct.
their data. Yeah, understood. Excellent. Good questions again. The follow-up from Mr. Howe was in general, I think we talked about that. That was the different centers and the projects. The follow-up from Harry, are there non-significant spaced feature evaluations like non-parametric feature ranks? That I have no idea.
Yeah, so I right now I don't recall on top of my head because I've worked on the paper 4 or 5 years ago, but we did ran like I think both parametric and non-parametric statistical test, maybe t-test or the non-parametric version of that. I don't recall exactly, but yeah, we actually followed that standard guideline, and we also talked to statistician at the time and making sure that yes, the method we are following is following the statistical process, and we got the recommendation from them as well to ensure that we are following the appropriate statistical analysis.
Excellent. So another follow-up from Christine is that's interesting. So do you think it's applicable beyond COVID, given it's based on deviation from normal conditions?
Excellent question. Short answer is yes. You can
Yeah,
apply the same understanding to any other condition. But as
sure.
I mentioned, these tests are not specific, they're sensitive. So take that with a grain of salt.
Right, right. Understood. And then another one from Nagin. Are you looking to use similar sensing technology to non-invasively measure core body temp, sorry, blood glucose levels, other physiology that's hard to directly measure, and what are the technical enablers of the sensor? Good question.
Again, great question. Short answer is yes. We are looking for multiple of those conditions. Uh, I can share more like offline because this is something ongoing work. I just wanted to share all the specific details that we are looking into the lab. But the short answer is yes, we are looking into different physiological condition. Just over the top, I can share that we are looking into cardiovascular health is a big thing. We are looking into cancer population. We are also looking into cardiometabolics as well. There are multiple ongoing study. Happy to share more maybe in a separate one-on-one conversation. I just don't want to share all the specific details right now. These are ongoing and some study that is under review in different grant panel as well.
Yeah, exactly. Excellent. And then the next isn't a question. It's just a comment from Harry. He's a big statistics guy, so that's why. But that's all part of it. These are excellent conversations. If there's no others, I have one question that I could ask, and it's back to the cardiac part. So the data, it's real common in my experience, like with any kind of electronic sensors, to be very good at looking at differential data, in other words, changes in data, and very hard to get an absolute answer. And so we talked about, the wearable sensors probably pretty good at monitoring changes in all these conditions, but maybe not as good as pinning them down to the exact absolute number. And so the way you would do that is to calibrate something, but how do you see that going? Because if you want to calibrate to the gold standard, that means somebody has to have the wearable and then have to wear the wearable and the gold standard device at the same time. So any thoughts on how you manage that?
That's the excellent question, and this is yes, really that what we this is a very good question in a sense that is a limitation that you mentioned.
Yeah,
That estimating changes is easier because you are
yeah,
using someone's own baseline and tracking that delta or the change. But
right.
estimating the true value is very difficult, and that is something we are tackling from more of the digital twin and generative factors idea, meaning that we want to understand how these signals are actually connected or associated both in this physiology and pathophysiology. Just to give you an idea that if
Yeah,
think about people with like I work a lot with heart failure and people with different cardiovascular condition. Like if their heart has certain anatomy and changes in anatomy with this condition, how that signal is changing over time. That
yeah,
is, we are trying to understand that like how those changes in cardiac anatomy and function is determining the changes in those signal and go back to that also like vice versa.
yeah,
So
yeah,
understanding that one-to-one mapping, that is something we are exploring a lot. And it's a very hard problem, as you mentioned, correctly pointed out. So this is one way we are working on that problem. Now,
yeah.
on the second question, like, okay, existing one, we can use or we can leverage this technology to track the change. How can you use that?
Right.
The majority of our current work is focusing on people who are has chronic condition. So they actually have multiple hospital visits to manage their condition. So what we do when they're coming, say from a certain visit, it can be baseline or some one visit in their routine, like 6 month or 1 year visit. So we can get that both their clinical data and our wearable data. So we can do that sort of calibration and we can use that calibration for the personalization to track their health in the real world. That is the way we are approaching this for
Yeah,
this
excellent.
interim period.
Excellent. Yeah, it's the population that matters more, right? And that's the
Correct.
one that you can solve better. That's a good coincidence, right? We got another one from Christine. I noticed that the population all had steps within a given range of 8 to 10,000 steps. So regularly active people. If this could be tested with a broader set of people with much more or less activity and still work, it would be a game changer for many diseases. So I don't, it's not a question. It's a, it's a great comment. Yeah. And then is data usually in a centralized location in your projects? Because I ask because federated learning, trading ML models from distributed data without sharing the data is usually mentioned for health related uses. I'm curious if this practice is useful.
Great question. Yes, we are also looking into federated learning as well as edge computing there. Like if
Mhm.
we don't want to share the data and there's a lot of security concerns, so we are also looking into edge AI, edge computing. What can we do in that? Another factor for us to consider, particularly in Arizona, there are a lot of people in the rural communities. They may not have very good connection to the internet or even no mobile network, right? So from them, what can you do with these limited resources? So something that we are also looking into that.
Yeah. Another one, Christine, last question, she hopes. Are you open to remote internships or only for full-time students? And then,
So this might be a conversation that we need to have. The reason is like when we a lot of time we work with like health related data, there's a lot of limitation
right,
with like what can we share.
right.
So that is like that is the main driving factor. Is like there's a lot of ethical approval that you have to go through, and because there's a lot of privacy and other factors that you need to consider. So that can have some sort of limitation, but we may need to have some one-on-one conversation on that to see the specific like requirement or the application, and then you can maybe figure out that whether a remote position might work on that front.
Yeah, so the best way to close the loop, and Harry's saying also interested. So the best way to close the loop to get people with follow-ups to you, should we point them to your LinkedIn maybe, or I
I
don't
have my
know.
email ID shared here, so feel free to, they
Oh,
can
it's
email
in
me.
there.
That's fine.
Okay. And you're okay getting emails there
I'm
in the
fine.
context of this.
Yeah.
Okay. And then, so anybody with questions, if you want to write down that email address right now, we will eventually get these slides posted. We have to make sure that there's nothing proprietary in them before we put them out there. But we would likely put these slides out there. And so it'll be out there, but that might not happen immediately. So write down the email address and send your follow-up questions. Um, I don't see any others from the audience, and we went over a little bit, so I think I'm just going to end it with a huge thank you. Me personally, at least, I found this exceedingly interesting and promising on both fronts, and just really awesome. And thanks for all the participation. We had, on the order of 20-ish people today. So that's a really good momentum we've got. So thank you again. Thanks all for joining, and hope to see you on the next one that we're going to do in a couple months.
Yeah. Thank you
Yep.
again very much for the IEEE EMBS chapter for giving me this opportunity. Thank you.
Excellent. Yep. Thank you all. Yep. Bye.